Okay, so in good tradition, 6 p.m., let's start. Thanks for coming to the lecture. And thank you for those at home, and hi to those at YouTube. Are there any questions at home or here? I'll actually spend the second half of the lecture speaking about the project. So we'll spend about ideally half an hour wrapping up the content of Unit 8. I know it's been very fast. And then about half an hour, maybe 25 minutes on the project. So we're obviously here in the last lecture. All right, so just a recap of what we did yesterday in the last lecture. So really a quick taste of machine learning and what machine learning is about, with a focus on supervised learning. So just some phrases. We've got those samples and observations. These are, you could think of them as, if you'd like, as the rows of this kind of big data matrix, and the columns are features. And we have a label that we're trying to predict, and that label can be a continuous value or maybe a discrete value from a finite set. Where in the former case, it's called a regression problem, in the latter case, classification problem. And we'll really stick to classification problems in what we do and also in the project. Then you've got this world of unsupervised learning. So we had a bit of a taste of that. Also, we looked at ML data sets, etc. So we looked at unsupervised learning a bit. Spent a bit of time with linear models. And this is a bit of a funny one in the sense that the actual learning process happens in this one command, the computation of the pseudo inverse. That's doable if A is not too big of a matrix. Otherwise, you have to use iterative methods anyway. And we saw that quite easily. We can get a classifier that gives us 86% accuracy on the MNIST digits. So it's trained on 60,000 digits. And when we test it on 10,000 more, we get this accuracy, and this diagonal is kind of what we'd like to be high in this confusion matrix. And these other numbers are numbers of misses out of 10,000. Okay, then we moved one step beyond and spoke about gradient-based learning and settled on these kind of slightly more complex models. And I know that some things were a bit vague there, but they'll still stay vague for this course. This is not a course of machine learning. This is a course of just programming in the context of multiple things. And in the context of machine learning, we're looking at these two types of models. So the first, the logistic regression model, is for binary classification, or you might say for binary probability or proportion prediction, but often you use it for classification. And you just take an affine combination of the data, X. So X would be your data, your vector of features. It's called your feature vector, if you'd like. And then you apply the sigmoid function to it. Okay, and that gives you a value between 0 and 1. So that is how the model predicts. And the training process is learning this B and this W. And the more general model, the softmax regression, sometimes called the multinomial regression model, etc., gives you kind of as a go immediately a probability vector of length k, okay, where k would be your number of types of labels. So in the case of digit classification, of course, k is 10. Okay, and you apply the softmax function to, again, an affine combination, only there's a bit of an abusive notation here, you might say. So in the first case, B is a scalar here, and here B is in general a vector. Okay, and W here is a matrix, and here little w is a vector. All right, so these were the models. And then we spent quite a bit of time looking at the actual training loop for logistic regression, and not everything was coded from first principles here. In particular, the gradient, for example, was computed using automatic differentiation, coming in this case with the Flux Julia package. And some other things that we didn't specify all the way, and I think that's fine. We could live with that. The loss function, for example, was also, from our perspective, a bit of a black box, the cross entropy loss function. Now, in tomorrow's, Thursdays and Fridays, and this week's practical, in the final practical, you have a full working example of this type of thing, training logistic regression, not softmax logistic regression, so just logistic regression for binary classification. And you're doing that you'll take a data set which won't be MNIST in this case, it will be fashion MNIST. So it has the same structure as MNIST, but it's not digits, but rather items of clothing. and you'll make a classifier that predicts if something is a sandal or a boot. Okay, very useful, sandal or boot. No, the concept is useful. So that's also will kind of give you a bit more background for the ML part of your project. And this is what an output of a training loop looks like. We looked at that. Then we spoke about fitting over fitting, which is a huge aspect of ML, both theory and practice. And more specifically with the data, there's also, we keep in mind that there's a training set and a development set, also called a validation set, would be a set that you would look at while you're tweaking your model or during iterations of the process. And the test set is really something that you keep on the side. So whatever you do on the test set should really kind of mimic what's happening with the unseen data. Okay, now, one thing I omitted yesterday, I'll speak about this for just a second, just so you know about it. There are cross-validation in general. Cross-validation is the general process of testing how your model works on the data. So one approach to cross-validation is just try the train set on the development set, try the train set on the development set, tweak something, try it again, try it again, try it again. That is one process. Sometimes you don't have enough data to separate a development set outside of the train set, and then you can kind of make a mock development set in the following way. So what you do is you split your data as follows. You say, this is for a second, and for this I equals 1, for this I equals 1, let's say that this pink thing is the validation data, where all these other bits are going to be training. And you will train a model based on that. But you will average this with another situation where you took another chunk. So maybe there'll be 10 of these chunks or 7 of these chunks, but not 1,000. And then the second chunk, you'll treat it as a validation data on which you didn't train your model, and you use the other blue chunks for training. And you do that for all capital K cases. Don't confuse this capital K with a number of classes. This is just that capital K can be 10 or 5 or maybe 3. And then you will just average the performance. So this can be some sort of performance, and you will average this performance over all possible K. So basically, every bit of your data played a role both of training and validation. That's a technique called K-fold cross-validation. It's quite popular if you don't have millions and millions of samples. All right, any questions up? This was a review of what we did, and now up until that bit? No, okay. All right. So now I just want to spend about 20 minutes on a completely different type of model in comparison to these linear models, logistic regression models, etc. In terms of your project, this model will only appear if you choose that as an option of task 3. So task 3 has 2 options, and you might choose to use this option. The reason we put it in this course, well, first of all, tree-based models are actually very useful. That's one reason, but we're not here to teach you the breadth of things that are useful in ML. The real reason we put it in is that they actually have a bit of a non-trivial programming aspect to them because they involve a recursive data structure, a tree. You've already dealt with trees in this course. For example, where have we seen trees? In homework. Tree? Yeah, homework in what? In what kind of data structures per se? Like the heap, right? So the heap, for example, the heap is a almost balanced complete binary tree, right? That's kind of the heap is this very kind of stylized data structure. And trees just appear, if you do more courses in computing, you might do a full course in data structures and algorithms. You'll see a whole bunch of ways in which trees are used. Trees can be used for sorting as well, and many other things as well. So a tree-based machine learning model also uses a data structure as a tree. It typically won't be a complete or an almost complete binary tree, but we'll see how that works. Now, from a practical perspective, tree-based models are actually when the whole trend of an area called what data mining was conceived, okay, maybe about 20 or 30 years ago, and that phrase has kind of died out, but you might still see many, many books about data mining. then tree-based models of data mining were very, very popular. Now, more importantly, there is a very powerful algorithm called random forest, which uses a forest has multiple trees, and that algorithm is still gives you kind of, let's call it, state-of-the-art generic performance. So when you're looking at data such as the MNIST digits data, it's very structured data. Random forest won't give you state-of-the-art performance. Neural networks beat that strongly. However, when you're just looking at tabular data and you want to make some predictions and you don't know anything else, so you don't have some very specific features of the data that you can use, random forests are actually very useful. And they're easy to use if you just use a package. So decision trees are the basis for random forest. Okay, so let's go through this quick whirlwind of decision trees and then random forests. So to do this, first of all, let's speak about data that only has two features. Okay, so not 28 by 28, not 784, only two features, just for demonstration. And let's take 3 classes, so not like MNIST 10 classes. And what we do here, okay, there's a whole bunch of code, but what we do is we just make some kind of random data. Okay, so we're going to deal at first with synthetic data, then we'll see how it works for MNIST, for an example. All right, so this function creates random data. It pulls a random from a multivariate normal. So we have kind of class 1, class 2, and class 3 based on the colors. So the red, the green, and the blue. And each one, when we create this synthetic data, we can specify its mean, vector, and covariance matrix. This is not so important, but this function make data, we're just going to use it again later because we'll take test data that uses the same function. So it kind of comes from the same process. Okay, but that's of course just a synthetic thing. This is not part of the ML process. One thing you might want to see just in this plotting has nothing to do with machine learning per se, but just the group option for plots. Grouping is kind of good. So then you actually get this nice plot where you group by the labels. So there are 3 labels. There's a label class 1, class 2, and class 3, and we're grouping by the labels, and the plot does it for us. So our purpose is now to create a classifier that will take a point in R2 in this case, because we have D equals 2 features in this case, and say for every point what it is. Is it green, red, or blue? Right, so I can pick some arbitrary, this is of course in train time, so this is my data, but later if I make a model, I can take this point, I don't know of what type it is, and I'd like the classifier to tell me what it is. Okay, obviously we'd like classifiers that are here to have, well, let me draw this point in a color like this. So if the point is say here, right, we'd hope that it's classified as green, as class 2, where if it's here, it's probably likely that it's blue, and if it's here, it's likely that it's red. Okay, so that's the classification task we have, the learning classification task we have with this data. So the way decision tree works is it is a tree where, assuming we had that tree, what it does is it tells you, well, at the root of the tree, let's pick one of the features, either the feature x1 or the feature x2, and split it someplace and say anything to the right of it is going to be of one class and anything to the left is going to be another class. Or alternatively, we would split it and we'd say anything to the right of it, go and look what's below, or anything to the left of it, go and look what's below. So there can be multiple splits. So just to see, I'll move a bit down to see what this thing can look like. Here's, for example, this can be a split on the data where we say anything to the right of feature 2 is, well, you'll go down and you'll need to decide. And anything to the left or below, sorry, not feature 2, x1, add the value 2, the first feature, add the value 2. And anything to the left, we'll say it's red. Yes. Oh, right. So the question is, how is this different than a regression model? Well, a regression model does something else. So a linear regression model gives you a predicted real value for every linear combination, whereas here, what we do, we're actually splitting. So, regression models as a model do not take the region and split it into different regions, right? It's just a different, it's a different way of splitting the decision space, right? Regression models just simply don't do that. We did say it very briefly yesterday, when we looked at this, said, oh, well, you can maybe put like a line like this and make a separation. But that's also not a regression model. In that case, that's a support vector machine. That's a separating hyperplane. So at the end of the day, it's all about a classifier. If you look at it as a deterministic classifier, it must take a point in the decision space, in this case in R2, and tell you what's happening. But the way decision trees do that are different than regression models, in the sense that what they do is you end up with splits, which can be, let's stop at this one for a second, which really split the region into sub-regions. Okay, that's the way it works. And the way it's recorded, the way your algorithm is recorded in memory, or the way, when I say algorithm here, algorithm is a misused word in machine learning. Sometimes the algorithm is a training algorithm. Sometimes people just call the model the algorithm, right? So, people say, hey, Facebook's algorithm. You guys don't know Facebook. You've heard maybe of Facebook. Instagram's algorithm, sorry. Instagram's algorithm, right? It's already the trained model. That's kind of the algorithm. Of course, their algorithm trains itself in parallel. It does active learning. It's not like a full separation between training and learning. But just what I'm saying is, here is already an algorithm which says, you give me a point in R2. So let's say the point is here. Like a point is an unseen data point that I've never seen before. I'm in production. The way it works is we will go, I know that this is a first split. It's going to say, is it to the right of the first split or to the left of the first split? It's to the right of the first split. Then it's going to go, okay, here's a second split in the tree. Is it, and if that second split is on this value of the second feature, is it above it or below it? It's above it, great. It must be blue. That's kind of what the algorithm does. Okay. Or the predictive model does. So of course, to implement this is a bit tricky, and that's kind of what's nice, because you guys dealt quite a lot with implementation this semester. So let's have kind of a rather quick look at the implementation. All right. So for this, let's first of all just define, in trees, let's define a node in a tree. Let's make a node which we'll call just so that's an abstract type, an abstract decision node. Okay. And a decision node is a abstract decision node. You've already seen this. Let's make it mutable so we can change it. And the real thing we have in a node is kind of the logic of feature. Which feature is this node going to split on? So what's the most important feature we split on, right? Is it going to be feature 1 or feature 2? So that's this integer. The integer is the index on the feature. And then the cutoff value is where to split. Okay. So it's really a decision tree, as you do when you make decisions, but every time you just look at one feature. And then, well, you're going to have, it's going to be a binary tree. We could have also had a version with a non-binary tree, but most common versions are with a binary tree. So you'll have a left child and a right child. And that child can either be another node that has more decisions, or it can be a leaf, right? We just say, right? So, if it's to the right of that feature, if it's an int, and that's a union. You've seen union before, right? So union is a type that's either this or that. Okay. Here's a function that prints this recursively. You've seen this type of function before for in the context of heaps and also in the context of types. So let's not dwell over it. It's sort of the same logic. So the show function from base, we're getting a method for it with these nodes, okay, and it calls itself potentially recursively if we have not gotten to a leaf. All right. And here, let's make a manual tree. So the tree, the root of the tree is a node in itself, and we'll say our tree takes the first feature as opposed to the second one. It's going to do a cutoff on 2. If we're less than the cutoff, we'll say that the class is class 1, the decided class is class 1, otherwise it's class 2. So if we this is now, since we define something, here is that object, and here is a show function for it. You've got a tree with 2 nodes, and that nodes are 1 and 2. And let's see if we had, before we do predict, let's just look at, here's that tree, okay? Here's 2, and there are 2 options. Here's a function that plots the decision row, plots the tree. Okay. So That's what it does. Now, to see how the plotting works, let's actually get the prediction function. So that will tell us a lot. So the prediction function has two methods. One method works on leaves. So if I predict on a leaf and that leaf is already in 64, I don't even care for what the data was. I've already walked down the tree and I've reached a leaf. So here you see Julia's multiple dispatch working nicely because you've got two methods of predict for that on nodes. However, if you're working on a node, then you do care what the features are. So this is the actual data point, right? And our example features is going to be a vector of length 2. But later when we do this with MNIST, it's going to be a vector of length 784, 28 by 28. And we say, if the features at node features is less than the cutoff, then make a recursive call on the left child. Otherwise, make a recursive call on the right child. The nice thing with Julia's multiple dispatch is that this predict recursive call can either call this bit of code, or if that left child, because our children were unions, either nodes or leaves, it can actually call this guy. Okay. So that's it. This is how prediction works. Here's just a helper function for accuracy. Accuracy is we're just going to predict on a data set. So the data set, it's quite common in this world to take capital X to be the data matrix of observations and features, and Y to be the vector of labels, hence the capital and the lowercase, okay? And if you're just going to predict, and if your prediction was correct, then count it as true, otherwise false, and then do a mean of all these Booleans, a mean of all the vectors of trues and false, and you'll get like an accuracy measure. Right, and here's plotting decisions, and this is how we plot the decision. Okay, so the way we plot decisions is we actually just in a very brute force way, we just go and we take a grid of points. We try on each point, and we apply predicting again and again and again and again. Okay, so we're not actually drawing these regions. We're actually every little point with very fine spacing. We're plotting the decision for them, and then we're creating a contour plot on the decision. Okay, it's kind of not it's plotting. So at most it's doing the number of pixels in a sense, or the number of steps there. So that's common when you look at classifiers. So you look at the data, and of course, right, so let's see, is this point I'm hovering on, is it classified correctly? Yeah. And is this point classified correctly? No, right? This classifier doesn't even give us class 2. But then we can add, so we can take our tree and let's just make another decision, right? By the way, people do this manually, right? They just make decision trees for kind of hierarchies of making decisions, right? So outside of the world of machine learning. So now we'll take the right child. The right child was this blue area. Before it was just 3 right child, right? Right child was just 3, but now we'll see right child was, it was 2. Why did I say 2? It was 2. It was the I think there might be a color issue here. So here we see right child is 1 and 2. I'm not sure. But anyway, the right child is the blue here. We'll replace it with another decision node, which will split now on the second feature. That's the vertical feature, add a cutoff of 4, and have a decision there. So after we've done that here, we just grew the tree. We just grew the tree. So the model that we supply is so different than models of like logistic regression, linear regression, or neural networks. It's completely different. The model is actually a tree, right? And these things run. People use them a lot in production and a whole bunch of things, both in business environment and in engineering, etc. and in science. So here now we've made this split. Okay, so like this green is classified correctly, this blue not, etc. And here, just for the heck of it, one more rule, and let's plot one more rule. So we now split this region into blue. So we can, in general, get kind of arbitrary large trees. Seems kind of good. Okay. All right. So we saw what we can do with trees. We can do that. Now, of course, with trees, we're going to have a problem. When we get to an arbitrarily large tree, it's going to overfit the data. okay? And that's where random forest will go and fix things. But before that, let's just very briefly see one algorithm for actually constructing a tree, because here we spoke about the tree data structure. We didn't actually have an algorithm for constructing the tree. So one rough way to do that, let's first of all rewrite everything. So instead of just having a node which is a decision, let's have a node which is decision with data. So basically, at each node, we will also keep a record of all of the data points that are its children. Now, this implementation we have here is wasteful. If you really want and you're doing that task in the homework, you can do it that you won't keep all of the data points. You'll just keep indices of data points. Okay, so like you see, this node as its children has just the data points that fall in it. So the data is kind of shrinking. Okay, and that's important for growing the tree. And this is like a leaf. This is what we'll do for leaves. Okay, so in a leaf, we would have liked, it would be great if all of the y's here are exactly equal to the value. That means a leaf that fully predicts its children. Well, we would have liked, assuming for a second, we'd ignore overfitting, but that's what we would have liked. So then when we look at decision nodes with data, they look just the same, but they just keep the data. Okay, and there's another, again, a show method for that, uses a previous show method, and a predict just uses, is the same. Okay, so the initial tree on some data xy, this is a function here, is just a decision node with data on all of the data we're given, and arbitrarily it just decides that the rule is class 1. That's just arbitrary. And we'll just make our tree an initial tree on xy. So now, if you do a different course, well, a proper course on machine learning, it's also been taught for times at UQ's advanced statistics course, then you'll actually see there are a whole bunch of theories, well, heuristics, let's call them, but algorithms on how to split trees. So how to grow a tree. Okay. We're just going to take a very simple method, which says, assume that your node now has these points. Well, let's just find the best possible split in this tree, in this subtree, in this green area. Look at the green area. So we have two things to choose. One thing is, are we going to split like this, like according to the first coordinate, and then maybe move it left and right? That's, well, that's the first choice, according to the first coordinate, or according to the second coordinate. That's like one choice. What's going to be the next feature that breaks this node that we're currently on? Because this node is currently like a green node, right? It's a leaf, but we're going to grow it to be beyond a leaf. The second thing is, let's say we decided that it's going to be the second feature, then we can do the cutoff here, we can do the cutoff here, we can do the cutoff here. There's basically a continuum of points where we can do the cutoff. But since data is finite, well, it's enough just to look at the data points and see where to do the cutoff on that finite number of data points. Okay, so what we're expected to see is now some heuristic which says, okay, let's say we decided that it's a second feature, where are we going to cut off? Okay, but let's also decide, is it the first feature or the second feature? So there are a few methods for this. Here we'll just do a method that says, well, let's do a cutoff. Let's do the next best cutoff at the point which minimizes mismatch in predictions on the left and mismatch of predictions on the right. Yeah, this is a lot. There's a lot of info, but it's just a taste of juice. Do you want to ask? No. Okay. All right. So here is this bit of code. It's find the splitting rule on a leaf. So you had some leaf. That leaf, was said on that bit of data that leaves on the leaf, that's on a certain class. Now let's loop over all possible features. In our example, it's going to loop only over 3. And within that, let's loop over all possible observations in that leaf. And all the time find the combination of J and I, which minimizes this. So I'm not going to go into the details, but that's essentially what's happening. Okay, that's essentially what's happening. And then we'll return, well, the feature that we've decided to choose, the cutoff, and what's going to be the prediction for the left and the right. And these bits, it's just which data goes to the left and which data goes to the right. Okay. So then when we build a tree, what we're going to do is we are going to recursively, we're going to build a tree on a leaf. We might specify ahead of time what should be the depth. So we don't want a tree that's too deep, perhaps. That's often the case, right? So we say, I'm only going to have up to 17 splits, for example. So if I have more and more and more and more splits, I'll say I'll stop. Okay. So we'll say what the depth is. And then we'll find this splitting rule, which is a minimization of this thing. Okay, this is the actual thing you're minimizing. I wouldn't call this a loss function because this is not loss-based learning. It's only loss within that very specific myopic decision of what we're going to split, left or right. And again, if you go into the theory of decision trees, random forests, you call tree-based models in general, you'll see that there are different different penalty functions here. Okay. And then what you're going to do is you're going to recursively call build tree on the left child and the right child. So this in its own right is kind of a recursive algorithm. And if you run this, well, if you run it without any limits, there we go. We get a highly overfitted tree. Okay, so this Picasso drawing here is a tree-based model, which predicts this training data with accuracy 1. Of course, it's not a great thing because go back to the analogy of this thing, right? This is like the polynomial interpolation of the data points instead of fitting a slightly more a less overfit model. Okay, so just some helper functions which we can do, just a bit more recursion, but I'll skip the code so you can count how many nodes are on a tree. Just do that recursively. This is some nice recursion. Okay, so num nodes, if you have a leaf, is going to be 1, but otherwise you just do adding down the road. You can also do a recursive function for the depth, right? So recursion galore. And if you call this function that, well, this is not a function, this is just a bit of code. What I'm doing here is I'm just again and again building trees where I'm building a tree with a depth of 2. Well, the maximal depth is what I allowed it. The actual depth is actually, well, it's 1 more than that, but that's okay. And it ended up having 5 nodes, and this was accuracy. So I'm actually running here and I'm saying, well, let's get deeper and deeper and deeper trees. So we allow more and more depth. Okay. So the trees get deeper, potentially deeper. The number of nodes grows. These are not complete trees, right? So in a complete binary tree, if you had a depth of 20, you'll have 1 billion nodes, 1 million nodes, 2 to the power 20, right? I mean, often these trees go very deep and not very, some nodes get left out. But what we see is that as we do that, the accuracy increases. And of course, at one point, the accuracy will settle at 1. So if we want to see this as an animation, just taking this, all these trees, this code runs, you can just take this run. So the way we make these notebooks, we just put them in this Julia Markdown, compile it. It takes a couple of minutes because this does a bit of learning, but then it runs. And then here's an animation of actually the tree, and you see the tree being built. Okay. Now, of course, when you get to these high training accuracies, even though it seems great, we're overfitting, right? So there should be some point where we stop. Maybe, we should stop at some point, right? Because at some point we're just so focused on this training data that any data that comes from a similar process that we haven't seen, the unseen data, would be abused and way off. So to see this here, let's actually just take validation data, which comes from the same synthetic function which we have, okay? So we specified, again, multivariate normal distributions with some covariance matrices and means, right? That this is a training data, this is a validation data. I mean, by design, you could see that they come from the same thing, right? So if we would use a tree that comes at the end of this process, which has a training accuracy at 1, it's not going to be very good on the validation data. Okay, And if you actually repeat this process and you run and what you see, this is a common type of curve that you see in machine learning in general, not just in the context of trees, is if you're increasing the depth. So this is like the complexity of your model. Okay, you could have also thought of it as in this axis, if you're in a completely different model, like in logistic regression, you're increasing the number of parameters, or in deep neural networks that we didn't speak about fully, you're increasing how many layers are, which is also called depth, by the way. Okay, so as you're increasing it, you see that your training accuracy, oh, great, it gets great. You're fitting, but your validation accuracy settles. In other cases, you can actually have a decrease because you're actually going to learn the wrong thing. So if you're actually doing this, and then you would probably like to stop someplace around here. Okay, so this is kind of the day job of the machine learner would be to do that. Okay, you can use trees for, yeah. Yes, yeah. So of course, people are trying to automate it, but machine learning engineer often stops at this kind of plots where the engineer actually goes and makes decisions. And decisions are in high parameter space, because first of all, you have models, trees, neural networks, logistic stuff, support vector machines. Then you have the hyperparameters of these models, right? And you need to kind of choose. Right, and then you have the specifics of these models. So they're not fully automated processes for hit a button and learn. People are working that, and it's improving over time. Look, for example, the H2O, which used to be a deep learning framework, but now they're trying to kind of automate things where they run all models for you in parallel and choose which is best. But it's not so easy to tweak. This is called tweaking hyperparameters. Yeah. Okay, so trees for. Yeah, so kind of the job, if you find yourself in industry working in machine learning engineering, right, you're kind of dealing both with this kind of statistical aspects, but this is rough stats, right? It's not kind of rigorous stats in that sense, because at the end of the day, you want to kind of deliver good accuracy on unseen data or good performance on unseen data, and you do touch a lot of code. All right, so trees for regression can also be done. We looked here at classification, auto regression. So if you actually want to predict a value, and in general, dealing with categorical features, both in trees and in all the other things, right? We spoke only about continuous features, pixel intensity, or a point x1, x2. But when you go to your project and you look at the Melbourne housing data set in the project, you actually have categorical features. Is it a house or is it an apartment? That's a categorical feature. But you don't need to do too much prediction in this project. You can just, then the last task, there's multiple linear regression that you should do from a statistical viewpoint. We'll speak about that in a second. Okay, so let's leave our tailor-made code. This is code that we just wrote for the course. But let's go to a package. So there are multiple packages in Julia. By the way, you should just mention here briefly XGBoost in general. This is beyond Julia. This is people don't say, hey, I used a tree. They say I used XGBoost. XGBoost is your off-the-shelf tool that just fits trees. Okay, but it doesn't just fit trees. It fits gradient boosted trees and random forest, which I'll speak about very briefly now. Not too much because I want to leave time for the project. So, but you also have a Julia package called decision tree, and also a few others in Julia. So here we see a decision tree. This is just, right, so the code here does not use the code above. We just connect to MNIST again. All right, 60,000 images, 784 features, and this build tree, but decision tree with a few hyperparameters you give it, is going to make a decision tree. It has about 3,000 leaves and it has a depth of 22. And if you try it on the training set, in this case, it'll give you 88% accuracy. And this runs rather quick. Okay, so you could use it, just use a package and use it. A machine learner in industry will not implement their own tree-based model. Okay, that's not, so that this is actually, this is to make this nice and efficient, and that's what's done in XGBoost. Since it's a recursive data structure, etc., there's no need for you to do that per se. But a machine learner in industry will write training loops day and night. That's probably a fair thing to say. Now, finally, because trees are kind of abusive and they overfit and you don't know how much depth to go, it's to take, etc., there are forests. The forest has many trees, okay? And what you do in a random forest, we don't have time to speak about this fully, but this is an algorithm that for a couple of years, around the year 2000, this was like the best thing in machine learning. And the fact is that for data sets that you still don't know what their structure is, and maybe if the data sets aren't great, this is still one of the best things in machine learning. So it has kind of a built-in non-overfitting feature. It kind of regularizes itself. I don't have time to speak about it much more, but what it's doing here is, this is called an ensemble. It's doing an average of little b trees. So you say how many trees you want in the forest. And what you do is each time it picks a random subset of the features to train on. A random forest is not great if you have 7 or 8 features or 2 features like what we had, but it's great for like something like images. Okay, although it doesn't use spatial connection in images, or it's really great for heterogeneous data sets. And it also does bagging, which just picks like random observations. And this is actually code from production code from the decision tree package. This is, we're not going to look at this code, but this build forest assumes you have a tree mechanism and it just builds a forest. So your task 3 in the project, if you choose to go on that path, and that's just a small little, well, small in terms of the weight, is to implement a random forest. You can use a production code as a guide, but this production code is multi-threaded. We didn't speak at all in the course about multi-threading. I'm sure Andy and Paul mentioned it, Andy and Paul Bellet here and there. So multi-threading, programs that run in parallel and things happen concurrently. I wanted to finish the content, and here ends Math 2504, but we'll speak about the project. Are there any questions? Okay, hope we didn't kill you. And the project shouldn't either. So let's look at the project. So we've got 18 minutes for the project. Now, just some administrative messages. So there are consultation hours Wednesday at 7:30 p.m. until, as usual, until the project is due. And this week, this is the final week of semester, there's still the consultation, the additional consultation hours. So one tomorrow, 4 p.m. with Alistair, and Thursday with me at 2, Friday with me also at 2. But next week, we are only limited from after semester finishes only to those, only to the 7:30 p.m. Wednesday. All right. Stop me at any point with questions. Also from the folks at home. All right. So what we did this year, first of all, just so you know, we've updated this today. I thought I did. I'm surprised that this isn't updated. I think maybe my web browser is caching stuff. So let me just open it like this. No, I'm wrong. Do you see 120 points here? So there are 120 points. Oh yeah, okay, and this is not on the other one. Yeah, okay. I just didn't update that, sorry. Okay, so just so you know, there's 120 points, but if you get more than 100, you just get 100. We truncated 100, okay? So just after looking at this, there's actually quite a lot of complexity. So those extra 20 can give you a bit of slack of doing this or not doing that, etc. And of course, the typical question, right? All 3 projects are in the course, but we replace the weakest of the 2 projects with the average of the weakest of the 3 projects with the average of the other 2. Okay, but to get a 6 or 7, you must pass all projects. Last year, you didn't have to do that, so some students didn't even submit project 3, right? But I mean, if you must submit project 3 and pass it to get a 6 or 7. That doesn't guarantee a 6 or 7, but it's a necessary condition. Okay, enough with that. So what we have in this project is standard kind of GitHub repo like you've done before. However, just in terms of coding, you're mostly creating scripting code. So the code doesn't need to be this super clean production code like you would have had for project 1 and project 2. Okay, I mean, things still need to be indented, things need to be properly named, etc. But scripting code is something that you change quickly. However, don't find yourself copy paste, like don't have all the same code for MNIST and copy it for fashion MNIST. You'll see what I mean in a second if you still haven't. The repo is the same stuff, but you're supposed to hand in 2 different Jupyter notebooks. So this is also different than the other projects. So these are 2 different Jupyter notebooks because this project is really kind of 2 projects in one. But these notebooks, just please print them and use the PDF merging utility to put them together. Everybody can find a PDF merging utility and merge the PDFs together. Don't worry about white space in terms of Jupyter notebook printing. All right, so the first task is similar to what we had last year, but smaller. And this has to do with, let's call it data science. Okay, so this has to do with Unit 7, with all the good stuff that Andy taught you at Unit 7, and that's housing price data. So you saw in Unit 7, I believe you saw Olympics, and there was also in the practical, there was data for university admission. So now you have this nice data set, it's housing pricing data. And this is not heavily specified. So in task, so take this data, load it into a data frame, overcome the trouble of dealing with missing values, because the missing values, so this is what students last year found sometimes a bit difficult, right? But this is the bread and butter of what many people would have to do in your day job at some point, right? The missing values, are there white space, are they capital NA, etc. So massage the data to do that. And then the first task is single variables. When I say single variables, a single column, house price or number of bedrooms, which is like a discrete thing, or a completely categorical one like house and apartment, and just do a bit of exploratory data analysis of that. Okay. The second one is exploratory data analysis, where you do plots of 2 different variables. But don't just throw plots with unlabeled things. The plots should be as nice as you can, right? You're really trying to describe what's in this data set. It sounds a bit simple, but it's a bit difficult because, you know, you got to go and adjust the figures and make them nice, et cetera, and plot and present the right things. So exploratory data analysis, when you get a data set, before you ask any real questions, just look at the data. How are you going to look at a data set with, I don't know, 30,000 houses sold and many, many variables? Well, some plots and some summary tables if you see fit. The third thing is exploratory data analysis over time, right? So these are different dimensions where you look at data, right? Over time, you know, you're talking about a time series of house prices over months and over days. And again, you need to use the right date ranges, the right presentation, et cetera. So a lot of details are in the presentation. As a resource, you don't have to, but feel free if you go to statistics with Julia, that's one example. For example, if you go to the gallery, there, then these are all the images of source that appears in the book. So say you like how this appears, not that these things are the most beautiful, then you can click the link and you get to the source. But there are many, many other examples. Okay, so just on how to present things. All right, the fourth task, subtask of this one, is to do a bit of linear regression modeling. So here, if you feel comfortable with statistics, if you've done a course or 2, I mean, you would have done this in Stat 1, 301, but if you've done a course or 2, etc., then try to make just a linear regression predictive model for house prices. And then you can present it. Well, you could assess your model in one of 2 ways. So one approach would be to actually split the data into a training set and a validation set. And then look, for example, at mean square error. That would be, you're not going to say accuracy, it's house price. So mean square error could be a cost. A different approach is use a more statistical approach and try to assess model fit using p-values. Of course, p-values on their own, when you're looking at multiple linear regression, p-values, each p-value on its own doesn't have a complete meaning, but still try to see which variables are significant and which are not. If you want to do something more fancy here, like lasso or ridge regression, go for it, but no need per se. So this is just a small statistical task summing up this kind of data analysis. So what you're to get from these kind of 40 points, oh, I see this is also a mistake. This 40 points should be 48 points. Sorry, I'll fix that. So that 40 is 48 because we added 2 points each year to make the 120, okay? So a total of 12 plus 12 plus 12 to 12, 40 points. So what you're to get by this task, later on, you might forget Julia, you might get a job, and you might be asked to do some analysis of data frames in R or pandas in Python, or maybe you'll choose to use Julia, and that's great. Then, you have some experience of working with CSV files. Okay. A student last year just finished this project, immediately got a summer job, and that's now their job, right? And they integrated Julia because that's what they knew in, CSV file manipulation, which is a big deal. Okay, questions about that one? No. All right, second task, and a home ask as well, please, if needed. So the second task is doing basic ML similarly to what we did now in the lecture. Not the decision trees, but rather the logistic regression and linear regression. But we're focused here on one small issue, which is when you have binary classifiers, so classifiers that only say if something is a digit 7 or a digit 3, but they don't know, they just know 7 or 3, how to convert them into a multi-class classifier. So there are two different approaches. So this is a type of work that you might do here if you're doing like a empirical machine learning research. Okay, so this is not research that's very analytical, it's more empirical, it's trialing things. You might do this in one of your honors projects or research projects or something like that. So this is kind of a warm-up for that type of thing. But it'll also give you experience such that if later you do enter a track that has some machine learning engineering in there, then you've done something. So these two approaches, let's explain them. So f sub theta I of x is a model that gives you a probability between 0 and 1, which says, is my sample x an I? Is it an I? Think of I as like the digit 7. Is it a digit 7 or not? Okay. How do you train it? Well, tomorrow and Thursday and Friday in the practical, you'll see logistic regression training, but we also did this for the linear model already with the pseudo inverse in the lecture yesterday. So assume you have, so let's say just for sake of clarity, capital K's, you have 10 digits, okay? So you have 10 models. The one versus all approach, which is just synonymous with one versus rest, you just have 10 models where in each model you trained one versus all the rest. One, is it a 7 or not a 7? Is it an 8 or not an 8? Is it 9, not a 9? And also 0, 1, 2, 3, 4, 5, 6. So you've got these 10 models. You choose the one that gives you the highest value here. Okay. That value can be either a probability or just an output of a linear model if it's not a probability. Sensible. So you've got 10 independent binary models. You've got just a model that was trained, the person who worked on that model, just kind of conceptually, never saw anything but digit 7 and non-digit 7. That person, she or he, they just thought that whatever's not a 7 is some other character, right? So they have that model. But then you have somebody who did it for digit 8, digit 9, etc. You're integrating all these models with this very simple rule. So you already saw a bit of this code yesterday on the linear model fit. That was the one versus all approach. The one versus one is the same idea, but it's just a bit more of a pain in the bum. Okay, but it can perform, as you might find out, a bit better, but it's also a more complex model, but maybe it won't perform better, you'll see. That will be your empirical result. So in this one, you have a model f theta ij. So that is a model, no, that's my thing. So that is a model that differentiates between a 7 and a 9, nothing else. It just saw examples of 7 and example 9. To help you in tomorrow's practical or Thursday or Friday in practical I, of course, the practical recordings are on Blackboard. Tina's doing that tomorrow. So in the practical, we're going to do that between a shoe and a sandal in Fashion MNIST. Okay, so it's like one model, a bit differentiating between a shoe and a sandal. So now you don't have, if capital K is 10, you don't have 10 models. You have, well, maybe 90 if you want, right? Because you don't need to compare a digit by itself, but maybe half of that, 45, because comparing I and J is like comparing J and I, right? you can either treat it as 90 or 45. Okay, better to think about it as 45. So 10 choose 2 is 45. All right. What you do is you then do all of the, so you want to see if it's a digit I, so think as I as 7. So compare I with 6, with 5, with 4, with 3, with 2, with 1, with 0, with 8, and with 9. Every time the sign of this comparison says it's a positive sample, okay, count it as like one more. So count how many you have here. I mean, the biggest that this thing will get would be k minus 1 or 9, okay? And then choose that one digit that won all the other competitions, okay? That's the algorithm. Questions about that one? This one looks a bit more complicated, but it's very well specified. Right, so it's you're using all of the pairwise comparisons, and these are really two different approaches that people have used over the years. If an algorithm is just a binary classifier, how do we make a multi-class classifier from it? Now, you don't have to use this, because when you look at an algorithm like logistic softmax regression, the one we spent quite a bit of time speaking about yesterday, well, not the model, but more the implementation of the training loop, the algorithm immediately gives you a probability vector with 10 options. And then you just choose the option that's most probable, okay? But I don't know, which is better? I mean, if you're given now, the question is, the empirical question, you're now given 2 data sets, MNIST and Fashion MNIST. Fashion MNIST is just like MNIST in terms of the size, 60,000 images, 10,000, 60,000 trained, 10,000 tests, and 10 classes. Only the classes are not digits, but rather items of clothing, okay? So, you know, this Fashion MNIST will have, I'm sure, worse performance in your results than MNIST, because it's harder to, I still don't know what a blouse means. What is it? Some piece of clothing. But, you know, so anyway, that's Fashion MNIST. Okay, so, all right, this is like your task. And then when you go to task, the first one, do the one versus all. Yeah, that's the easier of the two for a linear model and for logistic model. Now, you're really, tomorrow's practical, I just want to give a bit of tips here, or the practical this week does this for a logistic model. Okay, well, does it the base of it for a logistic model. However, there's a small subtlety. In the practical and the code we showed you, we didn't use explicit derivative expressions. We used big mechanism, automatic differentiation of derivatives. Well, automatic differentiation that then gives you a numerical derivative. Okay. What we're asking you here is to just use an explicit gradient expression. There are references to what they are. So it just means, so for the linear model, you can use it. We already saw an explicit gradient expression, but there are also explicit gradient expressions for the logistic and the softmax models. Okay, so that's what you can do in this task. In this task, you can do one versus one. So it's in a sense the same thing, but you need to do it, by the way, in each task, both for MNIST and for Fashion MNIST. And now it's one versus one. So here you're training 10 models. Here you're training 45 models, and each time comparing their accuracy on the test set. The third task, this one is almost yesterday's lecture, but again, just do it both for MNIST and for Fashion MNIST, and use an explicit derivative rather than the automatic differentiation derivative. And in the last task, just tabulate the results in some nice ways, right? So we have linear regression, logistic regression, which in both of them we do one versus one or one versus all. And we have 2 data sets, MNIST, Fashion MNIST, right? And we have softmax regression, which is not it's a multi-class classifier from the go. So that's that. I hope it's not going to be too difficult, but there'll be kind of a few challenges. I hope that the practical and the lecture give you enough help for that. Ask help, of course, if needed. So the last thing, this is just like a bonus, and you can, well, it's not a bonus. It's sort of, you can now treat it as a bonus since it's out of 120 points, but not necessarily. So option 1 is to augment the first task. This was also a question last year that a lot of students found troubling, but some students found it very rewarding. So just take the data and make a movie of the data on the Melbourne map of houses sold. It's kind of a cool thing to do. The hardships that students were finding are coordinate system, latitude, longitude is not the same as, you know, X, Y on the map, etc. But if you like geospatial things, then go for this. And the second option here, do one of these two. If you're doing task 3, I mean, you're asked to do task 3, but there's some bonus points. Okay. So the second thing is to do a random forest. So what we learned today, wrap that in a random forest, and also use that, your own implementation, well, wrapped on the implementation we have, or just improve and do from scratch, but you can use our example code, of course, on MNIST and fashion MNIST. So that would kind of augment these results with a completely different model. Okay, I hope it doesn't ruin your exam period, but rather add some joy to it. Any final questions, thoughts? No? Okay. All right, I'd just like to thank again to, especially to the industry lecturers, Paul Bellet and Andy Ferris, and also, of course, to Paul Verbeek from ITEE, and also to Amy and Metha and Anna for the perspective seminars, and almost most importantly to the 4 tutors, to Elaine and Tina and Alistair and Emma, and also to Thomas and Ivana that started with us. So the tutors really worked very hard this semester, and mostly to you students. Thanks. Thanks. Thanks.